Welcome to Spring LIB.
Hello everyone, so today we're doing chapter 11, problem 42, and we are asked to do some retrosynthesis again. So given these products, what alkyne will give you these products after hydroboration oxidation? So let's remember what hydroboration oxidation is. So if I have some sort of alkyne here, and I add my hydroboron, BH3, with my oxidizing agent, H2, O2, and OH minus, well, boron being very bulky would add on to the least substituted side of your alkyne. So I would draw my Hb3 as Hb2 with hydrogen bonded over here. So I would draw it such that the boron would fall right on top or right below the side of the alkyne which is least bulky. So the side with the more number of protons. So you see this side has one proton, this side has this whole hydrocarbon group here. So obviously it would be easier for boron to attack and attach on the least substituted side. So we would form the boron bond with this carbon, the hydrogen bond with this carbon, and then you would make two bonds. So you need to break two bonds. So this sigma bond breaks, one of these pi bond breaks. Now you would get your addition product. And remember, when you add an oxidizing agent, this would oxidize to an carbonyl group. And then obviously if we add another extra bond for this carbonyl with the oxygen up there, then we would have a carbon with 5 bonds. But that's not possible. So we know that this pi bond here must break as well. So that would give us, now the boron changes for oxygen, but it's a carbonyl because of oxidation. And we get our final product here. So this is how hydroboration works. So now, given the product, so let's start with A. So we have this aldehyde here. So we know that the boron replaces this oxygen. So let's work backwards. So we know that two things. Boron will attach on the least substituted side, and the oxygen the boron is replaced for oxygen. So I would add BH here, working backwards. I know that when I have the BH, I have a ketone, an alkene bond here. So now, before I were to add this boron, what would be my alkyne? Well, I would need an alkyne with less number of protons on this side than this side. So this side will be less sterically hindered than this side. So for example, if I were to have a proton here, and this side has one proton here, then I would need 2 protons here so that the boron can attach on this side. So we know that if I start with a starting material that looks like this, and you can also do this by trial and error, we know that this terminal position where we want the boron to attach has 1 proton, while this position where we don't want the boron to attach has 0 protons. So obviously boron will attach on the side with more number of protons, being the correct side as we predicted here with the starting material. So this would be the alkyne starting material for this product. Now let's see for B. So B, we're starting with this, so we need to work backwards. So we know that once again, the oxygen is replaced for boron. But here we have 2 possibilities. Your double bond can either be here or it can be here. So let's figure out which one is the correct choice. Well, if I were to do my double bond here, then I know that when the boron is, before the boron is attached, we would have an alkyne here. And then obviously we know that when we do counting carbons, this upper carbon here has 1 group, 2 groups, 3, 4, 5. So this carbon would have 5 bonds, but this is not possible. A carbon cannot have 5 bonds, so this route cannot exist. So let's try the route where we have our double bond down there. And then obviously when the boron is removed, we have our alkyne here. So everyone is happy here. We have 2 sides, 2 carbons with 4 bonds, and there's no protons added to either bond, so they're equivalent. So when we add our boron it would add with equal probability to either side to generate two products, one being this, and the other being, if it adds to the other side, being this. But if I count my carbons, you would see that these are equivalent. If I flip this, these are identical molecules. So we just drew two molecules that are exactly the same because it's symmetrical. So we know that, yes, this indeed is the correct product here.